a lot of people do not understand electricity and energy, and they get the two concepts very confused. So let's see if we can clear some of that up. Part of the problem stems from the fact that older models of electricity and energy teach it differently to how the current model teaches it. So older models might have said that we have electrical energy in the battery, and that when I press the switch, the light comes on, and that's because charge moves through the battery, trundles through. I've got an ammeter here measuring the current passing through it, trundles through this wire, deposits the energy in the lamp, and then the charge trundles back and picks up more energy. And you might have been taught that there is electrical energy in the wires, light energy coming out of the bulb, heat energy stored in the bulb, and then electrical energy, well, far less electrical energy, if any, for the charge that moves back, which then picks up more electrical energy by reducing the chemical energy store in the battery. And even now, I'm messing up the language because their older model that I've just mentioned doesn't talk about stores, it talks about types of energy. So even there, I'm messing this up. But that older model is not the current model that's used. Now, the problem is that there are still teachers out there who are taught with that older model and are therefore teaching it to the next generation. And that's fine. The model's fine. There's nothing wrong with it. It is just a model. It's not actually reality, but it's a serviceable model. It allows us to explain what's going on. It helps us with series circuits and parallel circuits, although there are some issues with it. But it's a perfectly good model. And that's what gets taught to the next generation, who then opens their textbooks or their revision guides and realizes that something different is going on, subtly different. Instead of energy types, like chemical energy, electrical energy, heat energy, light energy, instead of those energy types, there are now stores, which I accidentally used the word store because I'm so used to teaching the current model. So the current model teaches this. There is energy stored in the chemical energy stores of these batteries. In order for that energy to be transferred out of that store, there has to be chemical reactions, which means the transfer of charge. In other words, a current. If there is a current passing through this battery, then chemical reactions are taking place and the energy stored in the chemical energy stores of this battery reduce. Fine. If there's a current passing through this lamp, then energy is transferred to the thermal energy store of the lamp. And you can tell that because the lamp's temperature increases. And you can tell the lamp's temperature increases because when it's at a high enough temperature, it emits not just infrared radiation, but also visible radiation. So we have energy stored in the thermal energy store of this lamp. But the new model does not talk about energy in between the two. Now, there are problems with the new model as well. I'm not saying it's right. I'm not saying it's perfect, but it is what children need to understand. If there's no current passing through the battery, then no energy is transferred out of the chemical energy store of the battery. And if there's no current passing through the lamp, then no energy is transferred into the thermal energy store of the lamp. But we don't talk about electrical energy in the wires. We don't talk about energy being moved from the lamp via the wires, from the battery, via the wires into the lamp. We don't teach that. All we teach is that when there is a current, this energy store, the chemical energy store of the battery, reduces. This energy store, the energy store of the lamp, the thermal energy store of the lamp, increases. And if there's no current, as indicated by the ammeter showing 0, then there's no energy transferred out of this chemical energy store, and there's no energy transferred into the thermal energy store here. Okay, so that confuses students because they still picture energy as a fluid, a substance that moves from one place to another. So how can it be here 1 minute and then be here the next minute, but we don't talk about the energy existing in between? And I understand why that's a difficult concept. A better model about how energy transfers uses the Poynting vector, which is the cross product of the electric field and let's call it the magnetic field, H. Now that's very, very complicated. You have to understand some pretty advanced mathematics, basically the very top end of A-level mathematics, to follow what's going on with the Poynting vector. But it's essentially a vector that tells you the direction that energy is flowing. We don't say energy is stored in the electric field, although sometimes we do because it's convenient to do so. We don't say energy is stored in the magnetic field, although sometimes we do because it's convenient to do so. So when it comes to stores, we can only talk about the energy stored here and the energy stored here, but energy isn't stored in between. What's in between is, well, there's a current flowing, and that current transfers energy from here to here. But the current itself is not charge picking up energy. The charge doesn't carry the energy along. It's very easy to demonstrate that's the case. You can calculate how quickly the charge drifts through this wire. It's not very quick at all. And you can calculate, well, you can measure how long it takes between pressing the switch and the light coming on. Well, it's instant. There's no delay at all. So it would be incorrect to say that the energy has to be transferred by the charge, because the charge drifts through this wire incredibly, incredibly slowly. You can calculate it easily enough. It's called the drift velocity. And think of it like this. In the air around us, the air molecules are all moving very, very quickly, bouncing into each other, colliding. But if there's no wind in this room, then the drift velocity of the air molecules is 0. If there's a small breeze in this room, then there's a drift velocity of the air. Even though each air molecule is moving around at random very, very quickly, colliding with each other, the drift velocity would be very low. And, well, the air molecules are going to be moving at an average speed of about 450 meters per second. It's quite fast. But the wind speed outside, even now, is not 450 meters per second. It's significantly lower than that, probably not even 5 meters per second outside. So we're used to this idea of the drifting of air being called a wind. Well, that's what's happening in our circuit. The drifting of charge, our charge wind, is what is happening in these wires. Each electron, if I watch it, might be moving around very, very quickly, but the drift of them is very slow. And so to transfer energy from here to here by carrying it on that wind, well, that's not going to happen. And there are loads of attempts to make the old model work, to talk about electrons colliding with each other and transferring energy in a Newtonian way, but that's just not how it works. And that model actually causes more problems than it solves. So let's just talk about it again. The chemical energy store here can only reduce if there's a current passing through the battery, because this battery uses chemical reactions, which means there's the transfer of charge. Over here, energy is only transferred into the thermal energy store of the lamp if there's a current passing through it. Now, if I replaced this lamp with a superconductor, current could pass through it, but because it would have no resistance, there'd be no work done by that current. But there is resistance in that lamp, and therefore the temperature of the lamp does increase as energy is transferred to the thermal energy store of the lamp. And I could say the same thing about the wires, in fact. If I had superconducting wires, there'd be no energy transferred into the thermal energy stores of the wires. But actually, that is the case here. There is energy transferred to the thermal energy store of these wires. The wires have resistance. So there is energy constantly being transferred when there's a current into each part of this circuit. It's just the rate of transfer of energy into the lamp is higher because the resistance of the lamp is much higher. The current through each part of this lamp is through each part of this circuit is exactly the same. And why is the current through each part of this circuit exactly the same? Well, because charge is conserved. We don't lose any charge. This is a case of like a wind tunnel, but the wind tunnel is connected, so no air can leak out. So every extra air, in this case it's not air, it's electrons. Every extra electron I push in one side has got to come out the other side. It all has to drift around. We don't accumulate electrons anywhere. And what would happen if we did? Well, part of that circuit would become charged. And if part of this circuit became charged, then we'd feel electrical forces between that part of the circuit and another part of the circuit. And we don't see that. We just don't. And it gets confusing again, because if we talk about things like mobile phones, at the end of the day, we plug it in to charge it. Well, what are we actually putting into that phone? Well, it's not charge. As much charge enters that phone as leaves that phone. We're not actually putting any charge into our phone when we charge it. What we're actually doing is transferring energy into a chemical energy store within the battery of that phone. So the language we use, colloquially, is all wrong. And that's one of the reasons why students find this so challenging. There are only 5 energy stores that GCSE students need to know about. So we've got the idea of a chemical energy store and a thermal energy store. We also have an elastic potential energy store, and a gravitational potential energy store, and a kinetic energy store. And that's it. There are others. It's not an exhaustive list, but that really is it that we need to know about. And there are 4 ways of transferring energy. We can see 2 of them here. So one way is by a current. An electric current transfers energy. Another way is by the transmission of waves. This lamp is emitting infrared radiation. When it's at a high enough temperature, it emits visible radiation as well. That means that energy is coming out of that thermal energy store as that lamp radiates these waves. But the waves themselves aren't a store of energy. They're just another conduit, just another method to get energy out of this store. And where does the energy go? Well, ultimately, the light gets absorbed by the walls, the table, the ceiling, the floor, my retina in my eye, although that's a very small area compared to the rest of the room around me. So all that electromagnetic radiation gets absorbed in the surroundings and increases the temperature of the surroundings. That means it's increasing the thermal energy store of the surroundings. But the waves themselves are not an energy store. There's no light energy. There's no sound energy. There's no infrared energy. And if you say infrared is heat, then you'd have to say there's no heat energy. And that's why the word heat is so dangerous, because there is a thermal energy store. Is that heat? It's a clumsy word to use. So let's try and avoid it. So energy transfer methods, we've already got the idea of a current. No current, no energy is being transferred in this case. We've got the idea of waves, electromagnetic waves in the case of this lamp. There is also forces that can do work. Forces, pushers and pulls, they can transfer energy into or out of kinetic energy stores. You push something harder, you put more energy into its kinetic energy store. You stop pushing it, you're not putting energy into its kinetic energy store anymore. If you push it with the same force as the force of friction, then energy is coming out of its kinetic energy store at the same rate that we're putting energy in, so its speed doesn't change. And the last one is conductive heating. That gets a category of its own at GCSE level. The idea that if 2 bodies are in contact with each other and they're at different temperatures, then energy will flow from the body that's at a higher temperature to the body that's at a lower temperature. We do talk about energy flowing from thermal energy store to thermal energy store. But again, lots of revision guides and textbooks and teachers will talk about heat flowing from high temperatures to low temperatures. But the word heat is problematic. We use it in physics all the time. I don't want you to think the word heat is banned, just like the word electricity isn't banned. They're just vague words that we've got to be careful how we use. And at GCSE level, it's probably safer to avoid them. Not ban them, but just avoid them. Now, hopefully that clears up some of these misconceptions about energy in circuits. But I do want to emphasize again that this is a model. And it may be arguably a better model than the chemical energy, electrical energy, thermal energy, then light energy model. The chemical energy store and a current transferring energy into the thermal energy store, and then waves radiating, electromagnetic waves, reducing energy from that thermal energy store at the same rate that current puts energy into it. That second model is a better model, but it's still just a model, and there are still better ways of understanding energy in circuits that go beyond A level. And if you're interested, Derek at Veritasium did a fantastic video all about the Poynting vector and all about how energy in circuits really works. But the mathematics for that is at the top end of A level. So by all means watch it, it's very interesting, but just bear in mind it gets quite advanced for people who are, age 16, 15, 16, 17. They might find that challenging. All right, I hope you found that useful.